Okay, we're rolling. So what's going to happen in the first part of this section? We're going to talk about converting English into mathematics. And a good place to look for that is page 2 of your textbook. So there's a listing of words in English and how they translate into math on that page. For example, the word sum. That means you're going to add. So if we say the sum of x and 3, what that's going to mean is x plus 3. Now, we could have something like this. Let's say we're going to have the difference. The difference of 8 and 5. Well, that just means 8 minus 5. Now, subtraction, and that's what we're talking about here, that gets a little tricky. Let me give you another example. You'll also see this. Well, this is also 8 minus 5. Now, this one isn't in the text, but this is where it really gets tricky. You might see this. Five subtracted from 8. This actually means, again, 8 minus 5. So in the first two examples, the 8 was showing up first and then the 5. And so we do 8 minus 5. But in this case, we're taking 5 and we're subtracting it from 8. So even though in our sentence the 5 is being written first, still doing 8 minus 5. So that can be a little tricky when it comes to subtraction. Let me do a couple more. The product of x and y. Product means multiplication. And we're going to find, as you've seen in algebra before, and we're going to be reviewing some of this, there's lots of different ways to write multiplication in algebra. You can do x with the little multiplication sign, y. You could do x dot y. As all is multiplication. The most common one with variables is we just write them next to each other. X times y, x times y, x times y. Another way we'll write multiplication. We can put one of the variables or a number in parentheses. That also means x times y. Or we can put the x in parentheses. Or we can put them both in parentheses. Multiplication, there's a lot of different ways of expressing it with algebra. And this is one of those things we're going to run into. Most commonly, though, we're going to have numbers multiply the variables, like 5 and x. So if we're going to multiply 5 and x, what you're going to get is 5x. That means 5 times x. But you could write it as 5 dot x. You could write it as 5 little x and then the variable x. You could put this in parentheses. You could put this one in parentheses. You could put both of them in parentheses. It'll all mean the same thing, multiplication. So any questions about that? So I'm gonna leave those for you to do. So just page 2 is where you're gonna find those, what the different English words mean mathematically. Now there's one other kind of example. Let's see, let me do this one. It's a little more complicated. So let me make one point that's going to be really important. A number is a variable. So when we talk about an unknown number, that's what we mean by a variable. Now, you can think of this in terms of people. Let's say you're on Craigslist and you're looking for a housemate, and you put an ad out, say you have a room for rent, and somebody answers. Now you might learn their name and maybe a few interesting facts, but that's pretty much it. A lot of this person's personality, things that they're interested in, some things they might be allergic to or offended by. You probably don't know any of that yet. So when this person shows up to move in, the thing you want to be careful of is you want to treat them as a person. Now, you don't know which person they are in the 7 billion plus people that live on this planet, but they are a person. And that means there's certain dignities that we always reserve for them. Like, we wouldn't treat them like they were a dog. Like if someone came up to our door and they're like, hey, and you say, oh, that's nice. You start petting them on the head like they're a dog. You wouldn't want to do that. So keep that in mind. You want to treat them as a person. Now, of course, you might have a culture where you greet people by petting them on the head. But that's because it's reserved for people. And our Western culture, the one that I'm familiar with, we reserve that for pets. So I would not want to treat a person as a pet. So we want to treat them as a person. And the same thing is with numbers. Variables are numbers. We just don't know which one. So we can still add things to variables. We can still multiply things to variables. We can do all the things we do to variables that we would also do to numbers. We just can only go so far because we don't know. So if your housemate comes in, let's say you didn't learn their name for some reason. You can leave a greeting card like, hi, it's great to have you here. You're going to be off going to work when they arrive. But if you don't know their name, you can't quite go that far. You can say, well, welcome. And then that's it. You wouldn't want to try to make up a name for them. That'd be possibly really rude. So variables are the same way. We can try to add things to them. We can do all the things that we do with numbers, but we just can't quite carry it all the way through because we don't know exactly which number we're dealing with. So when we talk about a number, some mysterious number, that's a variable. And oftentimes it's represented by x, sometimes n. There's other variables we use, y, z, a, b. We'll meet a number of these as time goes on. So let me do the example. Two less than the quotient of a number and 4. Well, one thing we can do is we can copy edit. Now, 2 less than. Let's go back to page 2. This is one of those sort of unusual kinds of subtractions where even though the number 2 is first, when you take 2 less than something, that means you're subtracting 2 from it. If we wrote this in more familiar terms, you'd say the difference of whatever's going on down here and the number 2. So it's whatever's going on down here minus 2. So this is the first part. I'm sorry, the second part. We need to decode the first part. So this particular statement, the second part shows up first in the subtraction. It's just the way this statement works. And then the first part, the thing that's actually doing the subtracting, comes next. Well, let's figure this out. First off, a number. A number is some unknown number. It's a number, but we just don't know which one. So we're going to call it x. Now there's a lot going on in this part. There's the quotient of x and 4. So let's start rewriting this. The quotient of x and 4. If we look at page 2, quotient means division. So the quotient of x and 4, that means x over 4. So this is going to subtract the number 2. Questions about that? Let me do one more. So we have the sum of 7 and the product of x and y. Now, we want to be kind of careful here. We have the sum of 7 and. So we're going to take 7. We're going to add it to something else. But what are we going to add to 7? Well, the first thing, there's our 7 plus. Here's the second thing. What we're going to add to 7 is this whole piece here. The product of x and y. Product means multiplication. So x times y. And that's going to be our answer. Let me do one more, then we'll move on. And this one can be a little tricky. The product of 3 and the sum of x and y. So first off, we've got a product. We're going to multiply 3 and something else. Now, what's this something else? Well, it's this whole thing here. So what we're going to get is 3 times, and it's going to be multiplied to a sum. We want to be careful how we write this. We're multiplying 3 to the entire sum of x and y, not just part of it. We're not just multiplying 3 to the x and just 3 to the y. 3 is multiplied to the entire sum. That means we need to compute the sum first. And the way we do that is we put it in parentheses. This says, compute the sum first, then multiply it to 3. Now I'm using the little multiplication sign. I'm going to clean this up a little bit. 3 times x plus 1. And if we know what x and y are, then we can actually do this sum. Until we know what x and y are, we really can't do much. Though there is something called distribution. We'll talk about that later. There is a little something we can do. But that's what this would translate to. Any questions about that? So the other kind of problem we're going to look at, and this is section 1.1, there's a whole potpourri of things we're looking at. Algebraic expressions. So an algebraic expression is some combination of variables and numbers. And what we like to do is to find out the value of an algebraic expression. The way we do that was we're going to substitute the variable with some kind of number. So let me just review what substitution is. we're going to replace a variable with a number. Now, when we do this replacement, we're not just going to replace the variable one time. If the variable appears in many other places, everywhere we see that variable, we're going to replace it with that number. Let me do some examples. So we want to find the value of x plus 3 when x is equal to 7. So what that means, we'll take x plus 3. We're going to replace x with 7. Now this is a little convention. This is something mathematicians just do. But whenever we replace a variable with a number, we put the number in parentheses. You don't always have to do that. I'm going to stick with the convention anyway. You can think of it as saying, when you look at somebody's work, you can usually tell the variable that got replaced because there's a number with parentheses there. So you'll oftentimes see this. And you can really ignore these parentheses. We don't have anything that we're multiplying this to on the outside. So it's really just kind of for decoration. So this is just 7 plus 3. So your answer is going to be 10. Now let's do something a little more complicated. Let's say we've got this. Oh, yikes. A lot more complicated. Well, what this means is everywhere we see an x, we want to replace it with 4. So we'll rewrite this with each x replaced with 4. So now we can do the math. And one reason you'd want to use parentheses, where that is helpful, like it's not going to really do much for us here. We could have left the parentheses off. 4 squared, same thing. You don't really need parentheses here. Where they're helpful is this substitution, 2 times x. So we want to make sure we remind it it's 2 times 4. If we just erase the x and put a 4, it's going to look like 24. We don't want that. We want 2 times 4. So that's a good reason to use the parentheses, so there isn't any confusion. So this will be 16 plus 8 plus 8 over 6, or 32 over 6. And we can reduce that. We'll get 16 over 3. get a nice and proper fraction. So that's the idea of algebraic expressions. You're just going to replace the variable with some number, and just remember this is 2 times the variable. So we want 2 times whatever number we replace x with. And that's it. Any questions? All right. So next we're getting set builder and roster notations for sets. Now, for these problems, you got to have a little vocabulary. We're going to deal with types of numbers. So first off, they talk about natural numbers. Now, when we study the types of numbers, we're sort of looking at the history of human beings. I think the oldest artifact that has some indication of counting is a bone. It's a shaft of bone found, I think, in Africa, and it dates back 10,000 or 14,000 years ago. What's on this bone are little cuts, not butchery cuts, but cuts like someone's counting or keeping track of things. And so when we count, we oftentimes use our fingers. So we go 1, 2, 3, 4, 5, and so on. So these are called natural numbers. They sort of come naturally to us. And they go on forever. 100, 10 million. But they're numbers that don't have decimal points. They don't have fractions. There's no number 0. 0 shows up with whole numbers. Now, 0 is kind of a new thing in mathematics, to be honest. Its origins are in India, and it was independently devised in Mesoamerica. And the symbol, for example, in the Mayan society for 0 it's a shell. So on Mayan hieroglyphs, or if you're looking at dates on the Mayan calendars or stela, this means 0. So those are the whole numbers. 0, 1, 2, 3, 4, 5, and on forever. Next, you have integers. Now, integers, we just bring in the negative version of the whole numbers. So those are your integers. You come in from negative infinity, you get to 0, you go up to positive infinity. So what do negative numbers mean? For the number line, and if you might remember this from earlier algebra, positive numbers are on the right, and negative numbers are on the left. And that's all that they mean. Negative just means on the other side of 0. So when you have negative temperatures, if you have a temperature scale, these are your positive temperatures. And wow, we didn't make the scale big enough. We're getting temperatures colder than this. So we got to tack on ways of measuring how much colder things are compared to 0. Now, in temperatures, this has been revised. For example, we have the Celsius scale and the Fahrenheit scale, but you can still get negative temperatures. It turns out there's a scale called Kelvin, where there's an absolute 0. You cannot get a temperature colder than this one temperature. Now, in terms of Celsius, I think your Kelvin, I think it's negative 373 degrees Celsius, or it's negative 273 degrees Celsius. It's really cold, but you can reset the entire temperature system using this absolute temperature, the coldest it can get in the universe, and you can call that 0, and just have all the warmer temperatures, positive numbers, bigger than that 0. But if you find yourself having to go beyond 0, you can use negative numbers. So that's the idea of negative numbers. So natural whole integers, there's some other kinds. Rational numbers. These are all the possible fractions and ratios. You can think of fractions or rationals containing that ratio. So what are all the fractions? Well, you have your positive fractions, say 1/2. You have positive fractions that if you convert them to decimals, you get an infinite decimal that repeats itself. That means the 3's repeat on and on forever. You can have negative fractions. You can have improper fractions. Here's a really neat improper fraction. Any whole number, any integer, is equal to itself divided by 1. So you can turn any integer into a fraction. Give me the number 5, the fraction of 5 over 1. Give me negative 5 over 1. I can always convert integers into fractions. Same with 0. Zero divided by 1 is still 0. So these are your rational numbers, ratio, fractions. The irrational numbers. Not ratios. Sort of a way of thinking about it. So these are numbers that cannot be represented as fractions. So how do you write these numbers? Well, they exist in reality, so to speak, as decimals that go on forever without repeats. Now, I mean, 5 will show up, but there's not going to be a pattern in the decimal representation. It just seems to go on randomly. So, for example, pi. And we round this decimal off. to 3.14. But it actually goes on and on and on forever in a sequence of numbers that has no pattern to it. E. I wondered what this was on your calculator. Usually rounded to 2.71. And it goes on and on forever. Square root of 2. I think this is about 1.4. Goes on and on forever. When we work with irrational numbers, we represent them using one of two ways. Either we round them off, 1.4, 2.71, 3.14, or we represent them with a symbol, square root of 2, e, and pi. It's an interesting fact of mathematics that the most numerous, if you will, and that's kind of a tricky word because number means you can count. If you think about natural numbers, whole numbers, integers, you can try to count them. You could look at the natural numbers and say, well, they start out 1, 2, 3, 4, 5. But the whole numbers start out 0, 1, 2, 3, 4, 5. So it looks like the whole numbers have one extra number in them, 0. So there are more whole numbers than natural numbers. It's tricky to say there because since there's infinitely many, how do you count something that's infinite? There's some philosophical. This is when you socially distance with your mask on at the Starbucks patio, not indoors, and you have this conversation with your friend. The thing though with these integers, whole numbers, natural numbers, and rational numbers is you can come up with a process to count them all. And in theory, if you had infinite time, you would ultimately count, you would discover, point out every single one of them. The natural numbers, 1, 2, 3, 4, 5, and I just need more time to keep counting forever. Eventually, I'll hit every single one of them. Whole numbers, 0, 1, 2, 3, 4, 5, 6, and go on. And if I have infinite time, I'll eventually hit every single one of them. Or there's no way I can miss one. I might just stop counting that high. There's a way of doing this with rational numbers and integers. What's bizarre about irrationals, and this is sort of some pretty advanced mathematics, is you can show it's impossible to come up with a system or an algorithm that would let you count every single one if you had, say, infinite time. And you would always actually, whatever process you come up with to try to count all the different types of irrational numbers, your system or process will still cause you to skip over infinitely many of them. It's not like Pokemon. You can't get them all. So we tend to say that the irrationals have a denser infinity than the rationals. Anyway, diverging from that. We don't use them very much, but there's actually quite an impressive array, so to speak, of irrational numbers. Last kind. There's actually another kind, but we'll save it for later. Real numbers. If you take the rationals and the rationals are going to contain all the integers, because remember, all those integers, they're just improper fractions with the bottom number is 1. So the real numbers are the irrationals, or the rationals with the irrationals. In other words, if we take all the different types of numbers we've talked about so far and we dumped them into a box, that box we would say makes up the real numbers. It's all the numbers we could possibly use. Negative numbers, positive numbers, zero, fractions, numbers that can't be represented as fractions, but they're still numbers anyway. All those together are the real numbers. So any questions about that? There's a picture you can think of like this. We have our natural numbers. Natural numbers are really part of the whole numbers. The whole numbers just add zero to the naturals. The whole numbers are the positive version of the integers. And the integers, they're just the improper fractions with a denominator of 1 or a bottom number of 1 that's found in the family of fractions or rational numbers. But then you have these other numbers that are irrational. And then finally, you've got the real numbers. Which contains all of these. 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. All the possible fractions you can make out of these. Numbers that aren't fractions, but are still numbers, put them all together, we've got the real numbers. So that's where this is coming from. So when you get to these sets, finally, hopefully this will help help explain what they're talking about. So let's get back to these sets. If I'm going too fast, let me know. So sets. Sets are a collection of objects. Now this is new. If you took Math 097, you didn't see this before. Now a key thing about these sets, they don't have repeats. So let's say we have some numbers. One, two, two, three. If you want to convert these to a set, in the sets we use curly braces. We use 1, 2, 3. So the set of numbers that are in this list, the set would be 1, 2, 3. Now we have some special symbols that go with sets. It's this. This symbol, it looks sort of like the euro sign, the currency. This means is in the set. So let me explain that one. The number 1 is in this set. So we could write 1 is in or is an element of. That set. Now 5 is not in the set. So we would write our element of with a slash in it. 5 is not in this set, or 5 is not an element of this set. Now, when we list out all the elements in a set, we call that roster notation. So we just list everything out. So for example, if we wanted to do the roster notation of the whole, the whole numbers. We would do something like this. We would try to list all the whole numbers. Now, unfortunately, there's infinitely many. So I'm going to quit. I'm going to put dot, dot, dot. That means just keep adding in whole numbers. So that's one way we can think of whole numbers. There's another method, though, called set builder notation. Now, I'll probably get as far as this today, and then we'll stop for today. But set builder notation works like this. Let's say I want all the whole numbers, but from 1 to 10. Let's say between 1 and 10. So I'm just going to list them out. If I do this as roster, well, that's what they would look like as roster. Now, set builder notation, we're going to do this a little differently. We're going to do it more symbolically. So we want the whole numbers between 1 and 10. So this is what we're going to do. We're going to write it like this. Now, this is kind of peculiar, but you can say X. Well, let me add one more thing. Usually I'm going to write this inside here. I just got to kind of squeeze it in. There's a lot of formality in this. This means a number. So some number X such that that's really all this means. This is just sort of formality. It's not really helping you do a computation per se, at least not in this example. But there's a number x such that x is greater than 1 and x is less than 10, and that x is a whole number. This is how you could write this in set builder notation. Let me do another example. Let's say we're talking about even natural numbers. Now we can list them out roster-wise. 2, 4, 6, 8, 10, and so on. Now remember, the natural numbers start at the natural one, the number 1. So we can write it in roster format, or we can do it as set builder. So we always start out with this formality. The set of even natural numbers, we're talking about any number such that x is a multiple of 2. We could say something like this. Or we could say it a little differently. Now let me see how they don't get too complicated here. All right, they don't. We could do something like this. We could say an even number, well, all even numbers are divisible by 2. For x divided by 2 has no remainder. And since we're talking natural numbers, we don't want negative numbers. And x has to be greater than 0. So we could do something like that. But what it is, we have some number x, and then we have a description of what an even number is. So any questions about that? All right. Well, we're running out of time. It's 2:15. So what's left in this section? Well, we're going to talk about intervals. That means these symbols here. I'll mention an example on set builder notation next time we meet. And then we're going to jump into section 1.2. And 1.2, it's basically the rules of addition, subtraction, it's PEMDAS, it's these kinds of things. And then we should be able to get into 1.3 also. This chapter actually does go kind of fast, and it's a lot to throw at you. But if you have any questions about this, let me know, and we'll just go from there. There is one last example I do want to do with this, and this is what's more in the textbook regarding set builder. Let's say we have the set x such that x is irrational. So these are all the numbers x such that the number is irrational. It could be pi, it could be e, but it's all the irrational numbers. So that means pi is an element of this set, because pi is an irrational number. But let's take the same set the number 7 is not an irrational number. So we're going to put a slash through there. Because 7 is actually, it's a natural number, it's a whole number, it's also an integer, it's also a rational number. And we write it as 7 over 1, but it's not irrational. Because you can write it as a fraction, 7 over 1. So this is the type of problem you'll see in the homework. Anyway, that's it for today. So that's sort of the introduction. We spent a lot of time on the introduction. We're going to move a little faster in the future, but hopefully that gets you started on the homework section 1.1. We'll finish section 1.2 certainly on Thursday, and we'll just go from there. So if any questions, let me know. And other than that, have a wonderful afternoon.